Now that we've solved the big question, let's see some applications. A very nice application is linear regression. Let me show you what this is with an example. So which line, and lines are functions of the form f of x is mx plus b, best fits the data, and I'll just randomly put down some xy coordinates. So negative 1, 1, 1, 0, 2, 3, and 3, 1. Graphically, I have points in the xy plane, and I'd like to decide which line best fits them. So let me plot a few points here. So negative 1, 1 is here, 1, 0, 2, 3, and 3, 1. So which single line best fits this data? Here's how I'm going to think about it. Here's my answer. I want to plug in these x coordinates into my function f and get out the y coordinates. So I want to plug in the x values and get out the y values, hopefully on this line. So if I plug in the x values, so if I plug in negative 1 into my function, I get m times negative 1 plus b. If I plug in 1 or 2 or 3, then I get m times 1 plus b, or m times 2 plus b, or m times 3 plus b. I could take this right side of the expression and express it as a vector. So as a vector, I can write this as m times the vector negative 1, 1, 2, 3, plus b times the vector of all ones. Let me call that w. So this output is w. If I rephrase the original problem, what I really want is I want the vector w in the span of negative 1, 1, 2, 3, and all ones that is closest to the vector 1, 0, 3, 1. Now I got the 1, 0, 3, 1 vector from looking at the y coordinates, 1, 0, 3, 1. That's because I want this function to get as close as possible to the output values, the y values. This is the big question. This is the big question. I have to find the vector w in the span of others that's closest to another vector. This is what we know how to solve. So I'm going to solve this using the two-step method we outlined in the previous video. First, I'm going to apply the Gram-Schmidt procedure to these two vectors, and then I'm going to project. So applying the Gram-Schmidt procedure, so I'm going to start and I'm going to say u1 is my first vector, negative 1, 1, 2, 3, and I'm going to let u2 be the vector of all ones, and I'm going to take away just the right amount of component in the u1 direction to make u1 and u2 pairwise orthogonal. So I did the calculation ahead of this video. I think you get 5 over 15 times the vector negative 1, 1, 2, 3. And that gives me the vector u2 is 4/3, 2/3, 1/3, and 0. Now, all I care about the vectors u1 and u2 is that they have the same span as my original two vectors and that they're at a 90-degree angle. They're orthogonal. I don't really care about the length of the vectors u1 and u2. So instead, I'm going to take u2 to be the vector 4, 2, 1, 0, just because I don't like dealing with fractions. Again, the length of the vectors u1 and u2 don't matter, only the angle between them. So that's why I'm able to scale the vector u2 to avoid using the fractions. Then I can write down the vector w. W is the projection onto u1 and u2. So I'd do, for example, the dot product 1, 0, 3, 1 with my first vector divided by that first vector dotted with itself. That would be times this first vector. And I do the same calculation for u2, add them up. I don't feel like writing down that big thing now, but if you did and you summed the vectors, you would get 1/5 times 4, 6, 7, 8. Now I'm definitely not going to scale w. I definitely have to keep the fractions in w, because if I make w twice as long, then it's not going to be as close as possible to this vector anymore. So even though I scaled u2, warning, I would be wrong to scale the vector w. All right, so now we have that m, looking right back up here, m times -1, 1, 2, 3 plus b times the vector of all ones is equal to this vector w, which I found is 1/5, 4, 6, 7, 8. Now my real objective is to find the values of m and b. These are constants that I'd like to know so that I could draw my line. Now I have an equality here, so I have 4 equations and 2 unknowns. I've designed the vector w so that this is a consistent system, meaning that there is a solution to this set of 4 equations and 4 unknowns. So now you can solve 2 of them and find m and b. So I can solve, for example, -1m plus b is 4/5. That's the first row of this vector equation. And the second row would be m plus b is 6/5. So I have 2 equations and 2 unknowns. You can solve that and get the final answer. So then we find that m should be 1/5 and b should be 1. This gives me my answer. Now I have the m and the b, and therefore I know the function f, which fits this curve or these data points the best. I think I'll do another example of regression, maybe of a different form of the function, possibly a quadratic, in our next video. Please follow me along there.